Welcome to iTelescope. And my name is Christian Sasser. I'm the astronomer in charge for iTelescope. And I'm very pleased to welcome you all the way from the Perimeter Institute in Waterloo, Canada. Another Canadian, Dr. Luna Zagorac. And she's originally from Serbia, and she's been in the States before. She's going to talk to us today all about the things that you cannot see. So, Dr. Luna Zagorac, welcome, and very nice to see you here in our webinars. How are you?
Thank you very much, and thank you for having me. I'm doing very well, and yourself?
Very well. We're so excited to hear all about the things we cannot see. So it's going to be all yours. I'm going to be quiet now. Just let me know when you want to launch the polls, and I'll do that. Okay, thank you.
Okay, sure. So let me start sharing my screen, I guess. We can do it in that order, and then I will start my slideshow.
Yeah.
And can you just give me a thumbs up? Yes, great. We can all see this, hopefully. Okay, so thank you everybody again for coming and welcome. So what I will be talking to you about today is about the stuff that we can't see in the universe. And more crucially, this is the thing that my research is really focused on, why it might be fuzzy. And we'll talk about what that really means. So currently I am a postdoctoral fellow at the Perimeter Universe for Theoretical Physics. I just got my PhD in 2022 from Yale University in Connecticut. So I saw somebody is joining from Connecticut. So, I have opinions about New Haven pizza. Maybe drop yours in the chat if you have opinions about New Haven pizza. And I just really want to shout out Quentin Wayrich, who is at the Royal Astronomical Society of Canada at the David Dunlap Observatory in Toronto, for this really wonderful slide design that he did for a previous version of this talk that I gave. Okay, so this is a preview of the things that we will maybe talk about. So we will start with what we actually can see in the universe, right? That's extremely important because we have all of these wonderful detectors and telescopes and so on and so forth that tell us about all of this interesting stuff that exists here on Earth, but also in space. Then we will go into the real crux of what I'm interested in, what we don't see in the universe. So these are these question mark size things, right? Because we don't know what it is, we don't see it. But we will talk about one option for what it could be, and that covers why it might be fuzzy. Another way to state this question is, what if some of the smallest things were made up of some of the biggest things in the world? And we will get to that shortly. Okay, so let's start with what we do see in the universe. So the big things that we see in the universe. So these might be anything that you can think of when you just look up at the night sky with your naked eye, or when you use maybe one of the wonderful telescopes or anything like that. So these are things like planets, stars in our own galaxy, stars in other galaxies, newly formed stars, nebulae. Clouds of gas. Gas turns out to be really important. There's a lot of gas in space, and it's the thing out of which things like stars and planets are formed. We can even see galaxies about 13 billion years ago, especially with telescopes like the JWST that has recently launched and can see really, really far into the past. As of recently, we can even see our own black hole, if you've seen some of those images from the Event Horizon Telescope, and many, many more. So this is an example of what we can see with, say, JWST. So this is what the telescope looks like. And this is one of these really wonderful pictures that I am obsessed with. This is a region of the sky where we are currently forming new stars. So all of this gas is sort of a cradle for baby new stars that will form. And this is more of an example of what the really, really far away galaxies look like. So each of these little dots of light are individual galaxies very, very far away and very, very long ago that we can study. So those are really some marvelous things that are currently moving us forward. And of course, this is the picture of our own black hole from the Event Horizon Telescope, which is in fact not one telescope, but a bunch of telescopes all over the world working together to take this picture of the black hole that is at the center of our galaxy. So of course, you can't technically, this one is a bit of a cheat. You can't technically see the black hole. The black hole is sort of the lack of anything in the center here, but you can see this, what's called an accretion disk. So this is all of the gas and matter that's being thrown around by this black hole, and that is sort of circling it. it. And people that work on this stuff, including some at the Perimeter Institute, have like very precise predictions on what those rings and what that gas around us can tell us about the black hole in the center and about how gravity works. So that's some really, really exciting stuff. So now let's go on to some of the small things. The small things that you might think about are things like particles. So things like electrons, which are, at the crux of why we have electricity and know how to use it. Neutrons and protons, you might have heard of these sometime when discussing like electricity or atoms or stuff like that. Neutrinos are really wily little ones. They're extremely small and extremely fast. At all times, we are being pummeled by these little neutrinos coming out of the cosmos and our own sun and things like that, but they really don't like to interact. So they'll pass right by you and you'll never know. The fun fact is that all bananas are a little bit radioactive. So if you're closer to a banana, you might be feeling more neutrinos than if you're far from a banana, which is kind of cute. And actually, detecting things like neutrinos. So actually, we have somebody from Antarctica, so this is perfect. One way to detect things like some of these cosmic rays and neutrinos and stuff is at what's called IceCube, which is an experiment in Antarctica that drills all of these sort of fishing wires almost of photomultiplier tubes. Photomultiplier tubes are just these little devices that if they see a little bit of light, they'll magnify it so you see a bunch more light. And these things can trace sort of neutrinos going through something like this. So in this case, this is a muon, another type of very light particle that we can see sort of a neutrino goes through, it interacts with something. This happens very rarely, but it happens every so often. And you see all of these lights in these photomultiplier tubes. And this cube of these photomultiplier tubes is like a kilometer by a kilometer by a kilometer under the ice in Antarctica, which is pretty extreme. So maybe now would be a good time for one of those poll questions, maybe about how many particles we have ever discovered in the universe. Would that be all right? Yeah, there we go. I've sort of given the game away here because I've described, at least a little bit, but I would like to know how many fundamental particles, fundamental kinds of particles do you know have been discovered in the universe? So obviously I've noted at least 5 particles here, but are there more? And are all of these fundamental particles is a question that remains to be answered. So maybe I'll just let this little animation play for a little bit longer whilst everybody thinks about it. But this is a really important question because all of these particles built up everything that we see, right? Going back to what we see in the universe, you need all of these particles, which are really, really tiny, a lot of them, to build up all of the really, really big things in the universe. And also, things like you and me and your pets and your loved ones and stuff like that. They're really, really important. Okay, so maybe we can see the results. Aha, okay. Well, only one person said fewer than 5. That's fair enough. I listed 5 right here. The trick is that not all of these are fundamental particles. An electron is a fundamental particle, as is a neutrino. Neutrons and protons are actually made of 3 different types of quarks, which are fundamental particles in and of themselves. So I believe the answer is 17. There should be 5 bosons and 12 fermions, so-called. So whoever answered more than 15, pat yourselves on the back, you got it right. You might have heard of a really, really big, important boson that was the latest to be discovered at CERN sometime in the 2010s. I won't give away when, because that will be another question that we'll have. But good. So we've talked about big things. We're talking about small things. Now let's talk about something that's a little bit stranger, which is the wiggly things. When I say wiggly things, many things in the universe wiggle. They wiggle in interesting ways, but what I'm really interested in here is gravitational waves. So gravitational waves are sort of a different way of looking at the universe. It's not so much seeing, maybe hearing is a better analogy. And so this is what happens when really, really powerful events happen in the universe. So for instance, what we have in this video here is 2 black holes circling around another. They will eventually merge and form one bigger black hole. And these things are so heavy and they're moving sort of like disturbs the universe so much. They send out these ripples in space-time that we call gravitational waves. Then we have been able to detect again since sometime in the 2010s. Now, this is an extremely weird thing to think about if you haven't thought about gravitational waves before. It's like space-time bending. But actually, some of these places have done a really good job of explaining gravitational waves, such as the link that you see here. I encourage you to open it either now or later. But what you can get from this link and similar projects is what's called the sonification of a gravitational wave. So I wanted to play this sound for you here. I don't think it's transmitting through the Zoom, unfortunately. So if you're not hearing what I hear, it sounds sort of like, ooh. And it was once upon a time called the chirp heard around the world, because this is the sound equivalent of this. It is the sound equivalent of the waveform that is made in gravitational waves when these two black holes collide. So this happens in several steps. First, we have this inspiral, as was shown in the video of just they're sort of circling each other, sizing each other up. They start to get closer and closer, and you can sort of see the frequency of this wave get closer and closer. And eventually they merge. This is the peak of the wave, and then ring down is when they settle into a new black hole. So this is a really, really fundamental prediction way back from Albert Einstein, and confirming it was the last piece in the so-called theory of general relativity, which is our best explanation of gravity right now. Okay, so those are some types of things that we see in the universe. I will pause here and maybe we can do one more poll. So I've mentioned some really big discoveries that we've had recently, some really interesting and mind-blowing pictures and stuff like that. So yeah, what exciting discovery opened a new window into our universe in 2015 to 2016? I put both years in because the observation or discovery or whatever it was, or launch, technically happened in 2015, but it wasn't widely announced to the public until 2016. So first we have the earliest light in the universe, the so-called cosmic microwave background observed by Planck. We have the God particle, we mentioned that, also called the Higgs boson at CERN, which is the big collider living under Geneva in Europe. We have the first gravitational wave detection by LIGO. LIGO is the instrument that made the detection that I was just talking about. We have the first picture of the black hole by the Event Horizon Telescope, which we also mentioned. So again, I may have given at least part of the game away here because I didn't talk about one of these, but all four are really, really wonderful sort of observations, instruments, predictions, and really like crucial steps in evolving our understanding of the universe forward. So hopefully I've talked long enough to give you all a chance to answer. So maybe we can see the results in just a little bit.
By the way, I can assure everyone that Luna's singing of the black hole merger is much nicer than the original. So I'll share that.
Okay, so we have one person for the earliest light in the universe, the cosmic microwave background. So this one is a bit of a trick. I was being a bit cheeky with that one. So Planck is indeed a telescope that we launched into space that is seeing and observing the cosmic microwave background, and it's extremely important to our understanding of how the universe came from being really young to being the universe we have today. However, Planck launched, I believe in 2007, it was significantly earlier. But also Planck is not the first detection of the cosmic microwave background. That actually happened, I believe, in the 70s. It was either the 60s or the 70s. But I encourage you to look up the story because it shockingly has to do with pigeon poop. It's a very good story. The God particle, the Higgs boson, was seen at CERN in 2012. So it was a little bit earlier. And again, it was this magnificent crowning achievement of what's called the standard model, which describes those 17 particles that we've seen. But it's not the thing that opened up the new window into our universe. That was, as most people have answered correctly, in fact, the first gravitational wave detection by LIGO. So the first gravitational wave was seen sort of semi by accident during what's called the commissioning period of the telescope or of the instrument, when it was sort of listening for gravitational waves, but they were still, messing with a few things and making sure everything was all right. So it was seen in September of 2015 and announced sometime in spring of 2016. And then the last one was the picture by the EHT, which is again amazing, but not it's not usually called a new window, and that was more recent. I actually don't know what year that was. I could make something up, but it was, I don't know, between 2019 and 2021 or so. It was definitely more recent than LIGO. Okay, so now that we have all of that, let's talk about the things that we don't see in the universe. And I guess this was a wrong time to do the previous poll, because we need to do the third poll, because my next slide will answer that question. So maybe let's see, what do you think most of the universe is made up of? When I say most of the universe, I mean most of the mass or energy. To a cosmologist like myself, mass and energy are all the same thing. So what is most of the universe made up of, right? We talked about how gas is important. You form stars and planets out of that. Also stars and planets, obviously, we wouldn't be here without them. Black holes that we talked about, both taking pictures and listening to them, right? Or a secret fourth thing.
Yeah, that's a great poll, really. The secret fourth thing, what is that?
Yeah, again, I've slightly given away at least an indication of all of the answers here. But as you can imagine, we're talking about what we don't see in the universe, so there's some secret fourth thing to talk about. So maybe we can see the results when you get a chance. I hope folks have had a chance to choose one. Yeah, okay. So most people got the hint, hint, nudge, nudge, and it is in fact a secret fourth thing. We have black holes, which is a good guess because black holes are really, really heavy. And in fact, the secret fourth thing might be related to black holes in some people's ideas. That's not what we'll talk about today, but I'll mention it. And gas is actually another really good guess because there's more gas out there than you would think. So very good job, everyone. I'm proud of each and every one of you. But in the magnificent pie chart of the universe, the stuff that we don't see is actually quite a lot. So of all of the mass and energy out there, 70% is dark energy and 30% is matter, meaning that it has mass. It behaves like stuff, not like energy. And of that total matter, 80% is something called dark matter, and only 20% is luminous matter. So luminous matter is things like stars, galaxies, dust, gas, right? All of that stuff. But 5 times more matter exists out there, and it doesn't seem to interact with light. And that is something that we are really, really curious about. So in this talk, when we talk about what we don't see in the universe, we will specifically talk about dark matter. Dark energy is a whole other can of worms that people do study, and it's a very active area of study. But basically, what is the nature of dark energy and what is the nature of dark matter, I would say, are two of the, I don't know, I would say top 5 even biggest questions in physics and astronomy that we have waiting for us this century. And this is a XKCD comic that is a joke about dark matter because I love XKCD and I love dark matter, which says 2% milk fat is 2% milk fat, but whole milk isn't 100% milk fat, it's 3.5. Weird, what's the rest of it? About 27% is dark matter, the remainder is dark energy. So, to a cosmologist, that's probably true. Now, I'm telling you about something that we can't see in the universe, right? I'm telling you about this mysterious dark matter. I'm saying, trust me, there's some mass out there. It doesn't interact with light. We have no idea what it is, which seems like a hard sell, right? That seems like I'm asking you to trust me. So let me present to you sort of the original idea of why we think dark matter even exists. And it has to do with the way that things move. So one way to think about it is looking at sort of our own galaxy, but also looking at other galaxies and making observations. We can actually tell how fast things are moving based on some properties of the light, for instance, how different it is than like a light you would produce in like a lab by flashing a flashlight or something like that. And so you can make these observations that are in yellow and blue here. You can make observations from starlight, how fast the stars are moving. And you can also make observations from just hydrogen gas, right? Remember that the gas and the dust is actually quite important. There's a lot of it. And most of it is hydrogen, because hydrogen is just really easy to make in the universe, and there's a lot of it. And this is usually observed with radio telescopes and has a wavelength of 21 centimeters. So radio telescopes need to be really big because 21 centimeters is like a pretty it's a pretty big length of light, right? Usually we think of much faster light. And so these observations are very well understood, and they tell us about how say galaxies move, right? But they're not what we mathematically expect. If we just think about like a disk of light, which is a galaxy turning around, we would expect it to behave something like this. So this gap that gets more and more pronounced the farther away you go from the center of the galaxy, this gap has to be filled in with something. And it has to be filled in with something that doesn't shine. It's not interacting with light, we say, because we're just not seeing it. You can look for it all you want, but you don't see it. But it has to be there because we know how things move under their own gravity, and they just move like there's way more mass. And it's not a small difference that makes us think, oh, maybe our telescopes are miscalibrated. Remember, it's like 5 times more. So what does that mean? Where does the dark matter live? So if we're looking at a galaxy like this, we might imagine that this is our beautiful Milky Way. In this case, we live around here, about 8 kiloparsecs from the center. And so it has a halo around it, is what we call it. So what this disk is, it's made up of regular matter. I'm a cosmologist, so I might call it baryons. Particle physicists might be mad at that because that's not technically correct. But that is something that cosmologists say. So regular matter, luminous matter, baryons, those are everything made up of those 17 particles that we talked about, right? Things like electrons and muons, et cetera, et cetera. But around it, right, the farther away from the galaxy you go, the bigger the gap in that mass is. So there has to be something living around the galaxy that is like a sphere, and that is what we call a dark matter halo. So what I'm really interested in is studying what these dark matter halos are made up of, and what the secret particles, or are they even particles, that makes them up are. And so the thing why this is so hard to study is because there are a ton of ideas. A lot of really smart, creative people have thought about it for a while now. The first mention of something that could be interpreted as, dark matter is from Franz Zwicky, I believe in the 30s of the 20th century. So it's been almost 100 years of dark matter. But yeah, the question of what it is, that's the 10 million Swedish krona question. And in case you're wondering, that's what the Nobel Prize runs you these days. So if you figure it out, congratulations, you're going to have a really nice payday. And again, the issue of why it's so hard to determine is because we have this general understanding of how it behaves. We have a general understanding that there has to be a lot of it, that it lives around galaxies, especially around the edges of galaxies, and that it doesn't really interact with light. But there's a lot of ideas that could explain that, from these tiny, tiny particles called axions, a little bit more on those later, and all the way up to even weirder particles. And then this is again an XKCD comic. So some of these ideas are more jokes than real, but a lot of these ideas are real. The idea is that you can have it made up from like particles that are so tiny that they're way, way smaller of electrons, all the way to small black holes. But the smallest black hole, still much bigger than an electron. So that's sort of where black holes and most of the mass of the universe come together. So whoever answered that like most of the universe is made out of black holes, you could yet be proven right. We don't know. That is one option. One other option, of course, is the question of what if gravity is wrong? The idea that I presented to you is that things are moving differently than we know they should move under gravity, right? And so what if we just don't understand gravity? Which is kind of true. Of the forces out there, gravity is the one that we least understand. We have a least complete picture of it. And so what if on large scales, right, we live here on Earth. We're really good at knowing that if I trip, I'm going to fall. And I know that that's because of gravity. I have some intuition for how gravity works here on Earth, but that doesn't necessarily mean that it works the same as these super large scales. These are extreme environments that we don't live in. What if it's different? And again, a shout out to XKCD. This is not a completely ruled out picture, but it's not exactly favored. There's data that just doesn't really go with it. So it's a really, really wonderful idea. And I actually think it would be really exciting to find evidence for this one day. But so far, the observations we have, the data we have, just doesn't seem to favor it. Nevertheless, the search goes on. Okay, So that was a general introduction into the things we don't see, in this case, dark matter in the universe, right? And some of the ideas of what it could be. But now, and for the rest of the talk, I will, what's the word, prolastatize you on what I consider to be the best explanation, because I'm currently working on it. And the question that we will answer is, could dark matter be fuzzy? And the reason I pose this question this way is because there's an idea about dark matter, a dark matter candidate, so-called, that is called fuzzy dark matter. Fuzzy dark matter is made up of these super, super tiny particles that are called axions. You might ask, how tiny? So extremely tiny. So tiny that if you were to compare one of these axions, its mass, to the mass of an electron, that's equivalent to comparing the mass of an electron to the mass of a tennis ball. And you can see a tennis ball, you really can't see an electron, right? So it's incredibly small. It's, to my knowledge, the lowest mass particle that has ever been proposed as a explanation of dark matter. They are also a type of particle that is called a boson. That's a word that I mentioned earlier. You don't really need to know the details about them. All you need to know is that they like to cluster. They like to be together, especially if there's a lot of them. They like to sort of like smush as tight together as possible, as opposed to different particles called fermions, which really need their space. They're more individualistic. And so why does this matter? Why does it matter that it has such a small mass and that it really likes to cluster? It matters because that means that those dark matter halos that exist around galaxies look a little bit different if you assume that dark matter is fuzzy dark matter. So there is a dark matter candidate, so-called cold dark matter, which is just this generic description of dark matter. Let me assume as few things about dark matter as possible. Let me just assume that, it knows what gravity is. It doesn't really interact with the regular matter, and there's about a normal amount of it, or the amount that I expect from the observations. And I can run it forward and get these profiles of dark matter halos. So what a profile is, I'm looking at the density of dark matter from the very inner part of the galaxy on the left here all the way to the outer part on the right here. And so with cold dark matter, you get this gray line here. You see there's a break. So on the outside, it behaves like this, and on the inside, it gets denser way faster. And it gets dense so fast that at r equals 0, so at the very center of the galaxy, it actually tends towards infinity, which is not super physical. We don't like infinities in physics. They tend to be, more hypothetical than realistic. And also, this just doesn't quite jive with the observations that we have of certain dwarf galaxies that orbit our big galaxy, the Milky Way. Instead, fuzzy dark matter behaves the same way on the outside here, which is good. We like that. We think that that is a reasonable explanation for how dark matter behaves because it really matches the pictures we have of the universe. I call this outer part the skirt. But at the center, it forms this core, meaning that it actually goes to, some finite density at the center rather than like shooting up into infinity. And we like that. That matches our observations a little bit better. This core is also sometimes called a soliton for historic reasons. Now, the reason that this core really exists is because we have all of these tiny particles. There's a lot of them, and they really like to cluster. And they're so, so tiny, in fact, that some sort of quantum effects come into play. Now, this isn't actually a quantum system. It's too big for that, but you can talk about it in the language of quantum mechanics, which I think is really exciting. And so in quantum mechanics, the smaller a particle is, the bigger its so-called wavelength is, the bigger the uncertainty about exactly where the particle is. And so the reason we have this big cores is because the particles are so tiny that their wavelength is about the order of a kiloparsec, which is an inside of a galaxy, so really, really huge, farther than between like the Earth and the center of our galaxy. And these particles like to cluster in these so-called soliton cores. So that's a super different way of thinking about it than if you're thinking about generic sort of cold dark matter that we've been thinking about before. So this is sort of a sketch of what the halo looks like. What does it actually look like? So what does the dark matter halo actually, or a fuzzy dark matter halo actually look like? So when I imagine it as a sketch, I like to imagine it as a big sleeping kitty because I love sleeping kitties and they're very fuzzy. What it actually looks like is something like this. So this is a simulation that I have used in my research before. This is a halo that's forming through two blobs colliding. Don't really worry about what the blobs are. But the halo, like a slice through the halo looking down, looks something like this. So in the center, you see this yellow ball. That is that core. That's the thing in the center that we really, really like because it matches other observations better than cold dark matter. And what we have on the outskirts here is the fuzziness, the reason it has that name. So these are sometimes called interference patterns. And they're another thing that we're really used to seeing in quantum mechanics, which again is the study of like really small, tiny particles, like a single atom or something like that. And we're not used to seeing them when we study really big things like galaxies and their halos. So that's where that comes in. So because of this way of studying it, right, you have the core and you have this fuzziness, because the particles are so small that sort of quantum mechanical ideas become important in these really large scales, we can sort of start to think of one of these halos almost as a hydrogen atom. Right. So if you have a hydrogen atom, what you have is a proton in the center and an electron orbiting it. And when we do quantum mechanics, what we think about is so-called orbitals of the electron, which is we think of these shapes that depending on what quantum state the electron is in, it's most likely to be found somewhere in this shape. So if it's sort of at its lowest excited state, this is sometimes called the 1s orbital. You know, it's somewhere in this sphere, just around the proton. That seems pretty reasonable. If it's in this more excited state with some angular momentum, it's this dipole or a 2p, where it's, you know, on one of these bands where the proton is at the center. If it's 3D, it's even weirder. It's this sort of butterfly pattern, but that is where you are likely to find it. Now, an atom only has one electron, right? But here I don't just have one so-called axion, I have so many of them. Because if these things are so much smaller than electron, think about how big the galaxy is. Think about the biggest things that you can envision. The galaxy is so much bigger than that. So you need a whole lot of particles. And together, they sort of behave like this one orbital. They like to be in the same state because they're bosons, because they like to cluster. And so they behave in ways that are really, really similar to the hydrogen atom. So they can be in this super round orbital. They can be in this sort of dipolish orbital where you have two lobes, or they can be in this sort of orbital with the butterfly effect that is sometimes called a quadrupole. So that is what I study. I try to take these lessons from quantum mechanics and really apply them to these super, super big galaxies and what they like to look like. And I use that to ideally make some predictions that we can then compare with the data that we have and say, okay, does this explanation make more sense than other explanations for dark matter? Because remember, there's quite a few of them. So one example of an actual project where this came really in handy for me is by making all kinds of different halos in different ways. So I showed you one halo that I made by just colliding those two blobs, and then you get that like sort of fuzzy, weird halo in the center. But here I made like three or a few different kinds of halos, right? By colliding some different number of blobs. Maybe the blobs all have the same mass. Maybe some of them are bigger, some of them are smaller. Maybe they collide all at the same time. Maybe they don't collide at the same time. They collide in sequence. But what I did is I made these halos in this way because then I could very precisely control exactly what had happened to these, you know, synthetic halos in my code, and then I could make some inferences and try to apply those for like the much more real, much more messy halos that exist in the universe. And so one really interesting thing that I can do then is I can ask the halo, hey, how much of your total mass, how much of your total stuff, how much of the axions is actually in your ground state, that spherical orbital. And that's really, really important because that spherical orbital is exactly the core that we like to see. So what I am asking it is, hey, how big of a core do I expect to see in one of these halos? And that's important because if I want to prove that axions exist, or even if I want to say, oh, they probably don't exist, what I really need to know is how big that core is, because that is what I'm hunting for. That is the signature, that is the smoking gun evidence of this type of dark matter. And so what I could do in making all of these halos, I can then at every time, where time is on the horizontal axis here and time is in some weird code units, you can think of one as the total age of the universe if you like, but it doesn't really matter. I can ask it, hey, what percent of your total mass is in the core? And so, for instance, looking at the case n equals 2, where I just collide two blobs, so I have some halo of relatively low mass because it only has two blobs worth of mass. It's telling me none, none, no core, whoop, suddenly there is a core. So this is exactly where my halo formed. That is where those two blobs collided and formed that nice halo. And then I get some number that is oscillating around what, if you kind of squint at it, looks like a constant. You know, there's some up and down and it all over moves, but it always seems to be around 60%, 65% or so, which is not a bad approximation. And then for each of these higher numbers of blobs that collided, which basically correspond to just halos of higher mass, you get less and less of a percentage. So the more massive a halo is, the less of its mass is in its core. So that gives me some relationship. That tells me that, oh, if I can use this relationship to predict, knowing what the mass of our halo is, for instance, knowing what the mass of the Milky Way is, can I predict how big our core is? And so what you can do is use this, again, very small quantum inspired behavior to make this prediction. So what we have here is on the vertical axis is the relative mass of the core, MC, over the total mass of the halo. So again, this is what percent of your mass is the core, I'm asking the halo. And what we have on the horizontal axis is, don't really worry about these numbers, but it's basically some quantity that I've constructed out of the energy and the mass of the halo, because these are the things that I kind of think should describe my halo, right? And so I have some scalings, right? So if I want to know where the Milky Way falls on this, I can sort of calculate the energy and the mass of the Milky Way and find it on one of these lines and get a prediction for how big the core is. So this is one way of connecting these really tiny quantum mechanical, like single atom like effects and really applying them to the whole dark matter halo on these like most massive things in the universe, right? So this is an example how the smallest thing, how the smallest particle maybe ever proposed to explain dark matter has really big effects on like the biggest things we see in the universe, which are like the dark matter halos. So as a recap, we talked a little bit about what we do see in the universe, right? And this is where I got some of your opinions. We talked about the small particles. Remember that there are 17 of them. You don't have to remember that. I just think it's a fun trivia thing. We talked about some really, really big galaxies and how we can see them, in instance, in this image taken with the James Webb Space Telescope, and also about the wobbly things, the gravitational waves that opened a new window into our universe starting in 2015, 2016. We also talked about what we don't see in the universe, which is things like dark matter and dark energy, even though they are by far the dominant components of our universe, right? Together, they are like something like 95% of all of the mass and energy that is out there in the universe. Only 5% is known. So this is a really, really exciting time. And these are two things that, we as astrophysicists, cosmologists, physicists are really interested in detecting. And finally, we talked about why the stuff that we don't see in the universe, in this case specifically dark matter, might be fuzzy. So fuzzy dark matter, which is this dark matter made out of these tiny, tiny particles called axions, is one idea for what dark matter might be. And the way that I'm currently testing it is by basically treating the entire universe, or at least entire galaxies, like really big hydrogen atoms. So with that, I'm going to really thank you for your attention and ask for questions.